Hello, this video is going to cover Chapter 3 of our Introductory Chemistry class. It is titled Matter and Energy, which literally means that it's going to cover everything imaginable. Of course, we are doing this at an introductory level. So we're going to start with the matter side of the chapter. So we do have a lot of definitions, and one thing I want to point out as we move into this chapter is that for the most part, our chapters have a little bit of a pattern. We usually have a chapter that's pretty heavy with math, followed by one that's more conceptual. So chapter 2 was pretty much all math, and chapter 3 is going to be much more conceptual and definition based. They both have components of each other. So our math chapter did need some definitions, and our definition chapter does need some math. But just so you know, that seems to be how our textbook is balanced out. All right, so we're going to start with the definition of matter. Matter is anything that occupies space and has mass. So it's pretty much everything around you. And just kind of a heads up for where this is headed in a future slide, everything else is energy. So for example, heat and wind are energy, but you and the table and your phone are all matter. Matter is made up of atoms or molecules. These are the smallest pieces of matter that we can have. Atoms are very tiny particles. They're the building blocks of matter is the common phrase we use. The example that's over there is an aluminum can. And so those little spheres right here are representing individual aluminum atoms. Molecules are when we take atoms and we bond them together. And so the example that's on that slide there is methanol. And I know that because I can see the different colors. So really what we need to know is that the different colors are different types of atoms. So different atom types. And molecules are made up of two or more atoms. And these two can be the same type. So like the oxygen we breathe is an O2 molecule. It's two of the same type. Or it can be two or more different types. Water is H2O. So two hydrogen atoms and one oxygen atom. We're going to talk about a lot of different labels. Scientists really like to label and box things into categories. So we're going to label matter by two different ways today. One is based off of its physical state. And so our three categories here are solid, liquid, and gas. Now these states can change. We know this because we have experience with water. And water is the example we use in most of our slides because it is something we're so familiar with. So we're familiar with solid water as an ice, liquid water that we drink, and gas water or vapor when we boil something. When a substance is a solid, liquid, or gas, it's going to have very specific properties based off of how those atoms or molecules are moving around. And so we're going to start with looking at a solid. When we have a solid, the atoms or the molecules are stuck very close together and they can vibrate a little bit, but that's about it. When we have a liquid, the molecules or atoms are still stuck together really well, but now they can move past each other a little bit. They have a little bit more freedom to move around. And when we have a gas, the molecules or atoms are completely far apart and they have full range of motion to move around one another. So that structure is going to determine the properties that are on this slide. So our solid, their spacing, they're very close together. There we go. Their shape is that it's definite, meaning it doesn't change, the volume doesn't change, and they are incompressible, meaning they're already pressed together as much as they can, so we can't compress them any further. Liquid molecules are also close together, and their volume doesn't change. If you have a cup of water, like a measuring cup of water, and you pour it into your bathtub, it's still a cup of water. It doesn't now turn into a bathtub full of water. The shape is indefinite, meaning the shape can change. So you take that cup of water, it's in the shape of your measuring cup. When you pour it into your bathtub, it's now a flat puddle. But they are still incompressible. So because our solids and our liquids are both close together, that means that their volume and their compressibility are very similar to one another. The gases are the ones that are the most unique, and this is because the molecules are so far apart from each other. So because they're so far apart, that means that their shape can change, their volume can change, because that's going to be based off of how much space we're allowing them to have. And because they have so much extra space between them, that means that they are compressible. So you've probably heard of an air compressor. This is what we use to force air molecules into a basketball or a tire. It's compressing or pushing those air molecules closer together. Now, what the liquid and the gas molecules have in common is they both have some movement. And so because they both have some movement, that means that they can change their shape. And so that's what they have in common. Now, the gases have lots of freedom of movement, and so that's what allows them to have this indefinite volume and allow them to be compressible. And so they're unique compared to the other states. Solids do have a couple extra categories. We can label our solids as crystalline or amorphous. A crystalline solid is something that has a very arranged pattern, and this is something with flat faces, sharp edges, sharp corners, and this would be salt or diamonds. And then the other one is amorphous. Amorphous solids are kind of just like a pile of molecules. There's not a pattern or an arrangement to them. This is something that we can easily manipulate, meaning we can kind of bend it or move it, shape it into a lot of different shapes. So the examples are plastic and glass. With a little bit of heat, we can shape plastic and glass into pretty much any shape we need or want. So we've classified our structures, our molecules, our atoms, based off of their physical state. Now we're going to classify them based off of their composition. And so this is our flow chart here. We see that we have matter at the very top. We're going to start by dividing it into pure substances versus mixtures. And then our pure substances get broken apart into elements and compounds, and our mixtures get divided into homogeneous or homogeneous and heterogeneous. And so we're going to define all of those. The pictures that are on here are from your book. I think that they're great examples, and we'll talk about them as we go through. So we're going to start by talking about the difference between a pure substance and a mixture, and really it is what it sounds like. Something that is pure is made up of only one kind of piece, and we're using the word piece to be generic. So we're saying one kind of atom or one kind of molecule. A mixture is when we have different kinds. So the example of a pure substance would just be sugar. It's table sugar, that's all it is. It's a sugar molecule. A mixture would be if we took that sugar and salt and mix them together. So now we have sodium chloride or salt, and we have sugar mixed together. When we have a pure substance, it will always have the same ratio. So water is always H2O. It's always a 2 hydrogen to 1 oxygen ratio. It has constant ratios or constant percentages. Mixtures, though, can be very different. So if everybody in here made a cup of coffee, their sugar to coffee or cream to coffee ratio would be slightly different, or maybe very different, depending on how you take your coffee. And they would still all contain the same things, though. They would all still be coffee with cream and sugar, or however you take your coffee. But because that percentages can vary, that's one of our categories or descriptions of a mixture. So we're going to look at the two types of mixtures: homogeneous and heterogeneous. And it is often pronounced homogeneous. I do like to say homogeneous because it reminds us of the prefixes there. So we know that homo means same and hetero means different. And so it's a good way to emphasize what they are. A homogeneous mixture appears to be one thing. So even though it is a mixture of molecules or atoms, it will actually just look like one thing. So the example that was on our first slide was a cup of tea with sugar in it. So a cup of tea is going to have caffeine molecules, water molecules, sugar molecules, but you can't see that when you look at it. It's going to look like a light brown liquid, and it's going to appear uniform. A heterogeneous mixture is going to appear different or non-uniform. So the example that was on that first slide was oil and water. We can see the difference between the oil and the water. We can see that there's different layers, so we know that it's not uniform. So on the other side are the elements and the compounds. An element is something that cannot be broken down any further by a chemical reaction. So it is specific in there to say by a chemical reaction, meaning there's other ways to do it, but we just need to know that it is the smallest substance we can have. It can't be broken down further. Compounds are when we have combinations of elements. And so these can be broken down into their elements, but it would require a chemical reaction to do that. So a little bit more on those two. And the reason why is because we've had the word element and compound and atom and molecule, so it's important to know the difference between those two terms. The smallest piece of an element is called an atom. So if you have a copper pipe, the element that is made of is copper. In order to make that pipe, a bunch of little tiny copper atoms were combined together. So when we use the term element, it could describe any amount of that element, but the term atom is describing the smallest possible piece of that type of element. And that same definition or relationship applies to compound and molecule. So if we say that this is a glass of water, that's describing what compound is in that glass. And in order to have that water in the glass, it's made up of a bunch of very small water molecules. The difference between these words is not a big deal, but it is important to understand that they aren't exactly the same thing. So we're slightly switching gears here. We've talked about dividing matter into different categories. So now we're going to look at some of the properties of matter. And again, we have a couple categories. We can divide the properties into physical properties or chemical properties. And physical properties are things that we can observe or measure that doesn't change the composition of the substance. I'll give you a couple examples here in a second. Chemical properties are properties or characteristics that in order to observe them or measure them, we have to change the composition of the matter. It's not going to be the same thing when we're done. So if we think of gasoline, some of the properties we know about it is that it has a pretty distinct smell. It has a strong odor. Now, in order to know that it has an odor, We're just smelling it. We're not changing anything about it. So that would tell us that it's a physical property. But we also know that it's flammable. There's always lots of signs at the gas station warning you about its flammability. In order to know that it's flammable, somebody had to set it on fire. And when you set it on fire, at the end, it's no longer going to be gasoline. So its flammability is a chemical property. State changes, so going from a liquid to a gas, so like the boiling point. If we boil our gasoline, and so now it goes from being a liquid to a vapor, that's also a physical property. Now, it might seem like it's changing it, but it's still gasoline. It's still the same molecules, they've just taken on a new form. So our physical properties definitely include state changes. Solid to liquid to gas to solid, everything within that family. Now, I mentioned changing gasoline. We talked about burning it, seeing how flammable it was. There's different ways to change matter. And again, we have two categories. So our first category are physical changes. And physical changes will not change the composition of the matter. So this is very similar to our definition of a physical property. In order to observe a physical property, the composition doesn't change. When a physical, let me say that again. In order to observe a physical property, the composition does not change. A physical change is observed without changing the composition. So very similar. The physical change is referring to the change itself, whereas the physical property is referring to the properties we can observe or measure. So there's definitely overlap, but it's more like a noun versus verb thing. So our physical change examples on here are heating water, evaporating butane from a lighter. So here's our liquid butane. We hit the button on the lighter, so not the striker, but just the little button, and now it's in a gas form. It's still butane molecules. And dissolving sugar in water. So this one might seem like a big change, but really, the sugar's still there. If we evaporated off all the water, the sugar would still be in its same form. So the opposite then is a chemical change. And in order for a chemical change to occur, the composition has to change. And so this is also a chemical reaction. So our examples on here are iron that's rusting. When iron rusts, it's no longer iron. It's now iron oxide. Burning our butane. So now we're going to take our butane, we're going to hit that striker, and our butane burns with the oxygen in the air to create carbon dioxide and water. The butane molecules don't exist anymore. They've been turned into something else. And silver, when it tarnishes, it's reacting with the sulfur in the air to make a silver sulfide compound. So again, it's no longer just pure sulfide. So we've created new compounds through these chemical changes. It can be difficult to decide if a change that's occurring is a physical change or a chemical change. There we go. And one of the reasons it can be difficult is because when a chemical change occurs, it's also going to cause a physical change. If we burn something, if we burn our liquid butane, it's now going to look different. It's going to have new physical properties. So causing a chemical change will also cause new physical properties because we have a new substance. So a physical change is not going to change on the molecular level, just on the surface. Now, I mentioned the law of conservation of mass in Chapter 1. So this is a little bit more on it, kind of a reminder. But the law of conservation of mass says that matter is neither created nor destroyed in a chemical reaction. So again, we have our lighter. If we react our butane with oxygen, so we have 58 grams of butane, 208 grams of oxygen. So altogether, we're going to use 266 grams. It's going to produce carbon dioxide and water. 176 grams of carbon dioxide, 90 grams of water, 266 grams total. We can't magically lose mass, and we can't magically gain mass. It can only be converted into something new. I like to explain this or think of it like Legos. If you start with a house made out of Legos, you can take it apart and build a car made out of Legos. But the number of blue Legos and the number of red Legos and the number of yellow Legos is going to remain constant. You're not magically gaining or losing any Legos along the way. So we're switching gears. Our chapter was titled Matter and Energy, so we're going to move over to the energy side of the chapter. And we defined matter as anything that has mass and takes up space. Energy is anything that doesn't have mass or volume, so really it's everything else. The definition of energy is the capacity to do work, and work is defined as the result of a force acting on a distance. These definitions are fairly complex, and if you end up taking general chemistry or a physics course, then you're going to dive into these a lot more in depth. For this chapter, we're going to focus on the energy changes within a chemical reaction, and so we're looking at just a tiny portion of what energy is able to do. Now, even though chemistry is the study of matter, we have to look at energy because energy is what allows us to do chemical and physical changes. Just like we had a law of conservation of mass, we also have a law of conservation of energy, and it's very similar in its wording. It says that energy can neither be created nor destroyed. So that means that the total amount of energy that we have in the entire universe is constant. We can change its form. We can transfer it from one place to another. You can eat food to give you energy throughout the day, but we can't lose any energy and we can't gain any energy. When we talk about something being energy efficient, that means that we're using the energy in the best way possible. When something's not energy efficient, that might mean that it's very loud or it gives off a lot of heat. And so that energy is getting transferred into other forms that we don't want it to be used in. We have some categories. So our two main categories of energy are kinetic and potential. Kinetic energy is associated with motion. So we often like to show water going over waterfalls or through a dam. And so the kinetic energy is the water that's actually moving through the dam there. It's in motion. Potential energy is energy that is stored. So this is the water that's at the top of the dam there, ready to go. We also use sports analogies for this. So baseball, if you have a baseball bat and you have it up on your shoulder, ready to swing, it has a lot of stored potential energy. And then as you follow through and swing, that is your kinetic energy. Potential energy also can have a lot to do with gravity. This is not always the case, but these are good examples that we're used to seeing or that we have experience with. And then we have a handful of other energy types on here. So notice that the first three all fall into the kinetic label, and then the bottom two are potential. So we have electrical energy, which is a type of kinetic energy because it's the movement of electrons. Heat or thermal energy is molecular motion. So things get warm because the molecules themselves are moving around. And then light energy or radiant energy is energy transitions within an atom. So this is again electron movement, but in a very specific way. Nuclear energy is energy associated with the nucleus of an atom. So notice the name similarities there. And so it's stored energy or potential energy within that nucleus. And then chemical energy is within the bonds of a molecule or compound. And it's, again, that stored energy potential. So this is where we get into the small amount of math that this chapter has. And we're going to talk about how to measure some energy and how to measure temperature and then kind of put the two together. The most common unit that's used for energy is a calorie. Now this is a little confusing because we're used to seeing calories on nutrition labels. So we're going to define what a calorie is and then relate it back to food. A calorie is the amount of energy we need to raise 1 gram of water 1 degree Celsius. So 1 gram of water is about a thimbleful, so if you're so at all. And if we raise its temperature from 20 degrees Celsius to 21 degrees Celsius, that required 1 calorie. Now, that's not a very big energy change. It's a small amount of water and it's a small degree change. A kilocalorie, so we know that kilo is 1,000. So a kilocalorie is how much energy we need to raise 1 degree Celsius for 1,000 grams of water. So 1,000 times as much material. Food calories are kilocalories. So notice that a food calorie has a capital C. So 1,000 calories are 1 food calorie. And the reason why we have a different unit with the same name is because of the way it would look on packages. So if you have a bag of chips that's 150 calories, this is really 150,000 calories. Now, if you look at food bags from other countries, it will often just be written as 150 kilocalories. But because most of us weren't raised with the metric system, our labels don't say that on there. You might also see labels written in joules. So 1 calorie is equal to 4.184 joules. And then the last one down there is a kilowatt hour. So this is this is energy that's usually used in electricity. So if you look at your electricity bill, it will be in kilowatt hours. So it's just some handy conversions on here. We will mostly stick with joules, but we should be able to use conversions to go between any of our units there. When a chemical or physical change happens, it usually involves energy changes. And there's 2 ways that this can happen. The picture over here on the left has two parts. I'm just going to draw a little line here. So the top picture, we have our reactants. When we have a chemical reaction, our reactants turn into products. So we have our reactants and we have our products. So that means that as the reaction happens, we're going from a higher energy to a lower energy. The amount of difference between the energy of our reactants and the energy of our products is how much energy is released. And because the energy is being released, we label this as an exothermic reaction. And I often think of it as that the heat, or to be a little bit more generic, the energy is exiting the reaction. So exothermic, it's exiting or releasing. The example here, explosions. So really anything on fire, it's releasing energy in the form of heat. Glow sticks, they're releasing energy in the form of light. And then the bottom example is really the opposite. So here's our reactants, here's our products. So we're going to increase in energy as we go from our reactants to our products, which means that our reaction had to absorb energy in order for this to happen. And this is an endothermic reaction, and we can say that the energy is entering. Entering the reaction. And one good example for this is an instant cold pack. So the cold pack itself feels cold because it had all the energy is going into the reaction. So everything that's surrounding it is getting colder. It stole all of the energy from around it. So we use these words, heat and temperature. Oops, there we go. Heat and temperature often. And we know that they're slightly different in what they mean, but they are definitely connected to each other. So when we use the word heat, we're talking about the exchange of thermal energy. So thermal energy is a type of kinetic energy. It has to do with movement of molecules. And our heat is being exchanged between samples that have different temperature. Heat always travels from something of higher temperature to lower temperature. Temperature is a measure of the average thermal energy of the molecules in a sample. So if something has a higher temperature, that means that the molecules have more movement. And so we'll actually go back to that in a few other chapters to talk about how reactions are happening or help describe some behavior. So it's definitely a connection between the two. We have to use each other's terms to define one another. But for us, we're mostly going to be talking about temperature in these next couple slides as a way to calculate how much heat is being absorbed or released. So here's our three most common temperature scales. Move myself out of the way. There we go. We have Celsius on the far left, which the majority of the world uses. We have Kelvin in the middle, which is the scale that's used in science. And then we have Fahrenheit on the far right, which our country uses and is probably the one you're most familiar with. So these are arranged so that we can see how they're equal to each other. So up here at the top, we have 100 degrees. There we go, sorry. 100 degrees Celsius, 373 Kelvin, and 212 Fahrenheit, and that's the boiling point of water. Going down to that next one, 25 Celsius, 298 Kelvin, 75 Fahrenheit, that's room temperature. These are not numbers you need to memorize. It's just to give you an idea of equivalence between the scales, especially if you're more familiar with one or the other. At 0 degrees Celsius, 273 Kelvin, 32 degrees Fahrenheit, that is the temperature that water freezes at. The next one down, negative 38.9 Celsius, negative 38 Fahrenheit, 234.1 Kelvin. That's the temperature that mercury melts at. So mercury is one of our very few elements that is a liquid at room temperature. It's our only metal that is a liquid at room temperature. And that is when it becomes a liquid. So if we're colder than negative 38 Fahrenheit, then it would actually be a solid. The next one down is the temperature, the temperature that oxygen becomes a gas. So this is liquid oxygen. It's a very pretty light blue color. It's also very explosive. And then the very last number on the scale, negative 273 Celsius, 0 Kelvin, negative 459 Fahrenheit. This is called absolute zero. And this is the lowest temperature possible. So one of the big important things about Kelvin is that it does not have negative values, which is one of the reasons we use it in science, because it can prevent an equation from becoming negative if we have temperatures involved. Now we do need to know how to convert between these units. A Celsius and a Kelvin are the same sizes, but their scales are different. So where they start and end are off from each other. So because their sizes are the same, the conversion between them is pretty simple. Kelvin is equal to Celsius plus 273.15. A Celsius and a Fahrenheit aren't the same size. A Celsius is 1.8 times larger than a Fahrenheit, and they don't have the same scale. So the equation is a little bit more complex, but it's fairly simple algebra. The Celsius is equal to the Fahrenheit minus 32 divided by 1.8. So we're going to practice these. We are going to convert 139 Celsius into Fahrenheit and Kelvin. So we know that the Celsius is equal to Fahrenheit minus 32 divided by 1.8. So I am going to rearrange my equation first before I plug my numbers in. So I'm going to multiply both sides by 1.8. So now I have 1.8 times Celsius equals Fahrenheit minus 32. I'm going to add 32 to both sides. So now I have 1.8 times Celsius plus 32 equals Fahrenheit. So now that I have my equation equal to the correct unit, I can just plug in my Celsius value. So 1.8 times 139 plus 32. So I put that into my calculator, and my calculator says 282.2. So just like in chapter 2, we want to do a couple things with this number. We want to check our significant figures. Now, 1.8 and 32 are part of the equation, so we're not going to include those. We just want to keep the same number of decimal places as we started with. So we have 2. So we have 3. I was looking at the wrong number there. We started with 3, so I'm going to keep 3. So this is going to round to 282. And we know we're ending with degrees Fahrenheit. And then we're going to do this again, but going from Celsius to Kelvin. And we know the equation is Kelvin is equal to Celsius plus 273.15. So we don't need to do any rearrangements this time. So this time we can just plug in our value. Our Kelvin is equal to 139 plus 273.15. And we get 412.15. And again, we want to check the same information we would if we were doing any unit conversion. So we started with our last value in the ones place or 3 decimal places. So I'm going to end it right there. So we get 412 Kelvin. So what that tells me is that these 3 numbers circled in red, 139 Celsius, 282 Fahrenheit, and 412 Kelvin, are all the same temperature value. So our last topic in this chapter, we have a couple slides left, is looking at heat capacity. Heat capacity is how much heat is needed to raise the temperature 1 degree Celsius for an object, for a substance. And the value that we use more often is the specific heat capacity, which is how much heat it takes to raise 1 gram of that substance 1 degree Celsius. The units are kind of complex here. The units, though, are incorporating all parts. We have the heat represented by joules or calories. We have the mass represented by grams, and then that degrees Celsius in there for the temperature change. We have a table on the side over here showing us the specific heat capacity of a lot of different substances. And the one I want to point out is water. Notice how high water is compared to all of the other substances. Water's heat capacity is 4.184. So that means that it takes a lot more energy to actually raise the temperature of water. When you boil water, you know that it takes quite a long time, and this is one of the reasons why. We have to give it a lot of energy in order for it to get hotter. This is also the reason why cities that are closer to the water are cooler than cities that are more inland. I live in Long Beach, less than a mile from the beach, and the temperature at my house is always about 10 degrees cooler than when I go to school. Because Orange is so far inland, it has less moisture in the air, so it warms up a lot faster. I don't think I have glass on this list. Another example, though, is glass versus aluminum. So if you bake or cook and you've used a glass pan in the oven versus a metal pan, you know from experience that glass cools down much more slowly than an aluminum pan. And again, that has to do with the heat capacity. And it can even change how long you need to cook something. Something in a glass pan will actually need to cook longer because it takes longer just to warm the glass up in the first place. So we can put all this information together. And this is our equation that we are going to use on our next and final slide. The amount of heat energy that is gained or lost by a substance depends on three things. So the heat energy is defined as Q. And the three things it depends on is how much material there is, or the mass, what the material is, and we use that specific heat capacity to define what it is, and how much the temperature changed. So right there we have delta T. So the little triangle is delta, and delta T or delta anything means change in, and when we're calculating the change, we always want to do final minus initial. So delta T is the final temperature minus the initial temperature. And our Q value, if it's negative, that means that we have lost heat and it is an exothermic reaction. And if we have a positive Q value, then that means the heat has been gained and it's an endothermic reaction. Now the mass is never going to be negative and the specific heat capacity aren't going to be negative. So this is based off of the temperature change. So if Q is negative, that means that our temperature change is negative. And if Q is positive, that means our temperature change is positive. So we're going to use this equation on the next slide. So here's our next and last slide for this chapter. Our slide says a lead weight absorbs 11.3 joules of heat when it warms from 26 Celsius to 38 Celsius. What is the mass of the lead weight? And then we have C lead equals 0.128 joules per gram degree Celsius. So let's just kind of rewrite the information we have and give it the appropriate labels. So we're starting off with it absorbing 11.3 joules of heat. I know that that's Q. And I know that for two reasons. One, it's telling me that's how much heat was absorbed. And two, it has the units joules. So both of those have to do with Q. We know that the temperature goes from 26 Celsius to 38 Celsius. So we know it's starting at 26, so that's my initial temperature, and it's ending at 38, that's my final temperature. We're also in there, it says, what is the mass? So essentially, I'm making a list of my given information, excuse me, and the information I need to find. And then that last piece of given information is the specific heat capacity. So notice it's written as C with the little word lead there. So it is saying that this is the specific heat capacity for lead. And from our last page, our last slide, we know that Q equals mc delta T. I don't think I actually pointed that out, but that equation is down here on the bottom of the slide. So we have the words telling us what each of those variables mean, and then the variables themselves. So Q equals mc delta T. We are solving for m, so I'm going to do a little bit of rearranging there so that we can have it say m equals. So I'm going to divide both sides by c delta T. So Q divided by c times delta T is equal to the mass. So really, we can just plug in our values. Now there's one piece of information we're missing. We don't actually have delta T. We have enough information to get there though. We know that delta T is final minus initial. So 38 minus 26, our delta T is 12 degrees Celsius. So for my equation here, I'm going to put 11.3 joules on the top, 0.128 joules per gram degree Celsius on the bottom, and 12 degrees Celsius on the bottom. Now, we know we want to check to make sure units are canceling out. It's a little bit more complex than what we did last chapter, but we can see that our joules will cancel and our degrees Celsius, and we're left with grams, and we're left with 1 over grams, so we have the reciprocal of our fraction. But when we calculate this out, our calculator tells us that it is 7.35677 grams. We figured out our units, we checked our units. There's not really a way to check the size of the number because there's too many variables going on. So we can always, redo the math and make sure that that's good. But the last thing is significant figures. So we have 3 significant figures, we have 2 significant figures, and we have 3 significant figures. So 2 is our winner. So that's where I'm going to cut it off. I look behind, and this is going to become 7.4 grams. So as long as you have 3 of those variables, you can solve for the 4th. All right, that is it for Chapter 3. Thank you.